Jack Michael, and this is Physics 2212, Lab 4. Brief table of contents of what this lab will be covering. We'll have an introduction, a data and observation section, the code from the closed script, a discussion and conclusion. Introduction, the purpose and fundamental principles of this lab. The purpose of this lab is to see the influence of magnetic field from a bar magnet and predict how this influences different observation points using the Biot-Savart law. So pretty much how distance affects the magnetic field of a bar magnet. Preview of their results. Bar magnets have a magnetic dipole which moves objects in the direction from south to north on the parallel axis and north to south on the perpendicular axis. The Biot-Savart law. So this law acts as a relation of magnetic fields to the currents of the source, seeing how charge, density, and distribution influences the force on surrounding points of observation. This equation can be also altered to account for magnetic dipoles. So this equation is shown here on the bottom. The experimental model, so pretty much we're using the phone magnetometer app with a neodymium bar magnet to see the effect of distance on the magnetic force. So the surroundings are the bar magnet. The magnetic field of the Earth should also be considered in the surroundings. The magnetometer sensor. The sensor first needs to be zeroed out on the north to south axis, and then the east to west axis. Tape the phone on the meter stick where both are zeroed to make sure the influencing magnetic field is zero. Distances and magnetic fields. Distances need to be collected for the locations where the magnetic field were 270, 120, 170, and 220 micro Teslas, which is the unit for magnetism, which we'll be using. And these were used in the perpendicular axis magnetic dipole equation to find the magnetic field influence seen on the previous slide. So here's the data we collected. So you see as the distances decrease between R2070, they're decreasing as the magnetism is going up. So as distance goes down, magnetism goes up. Yeah, that's also a similar sort of thing seen on the off-axis field data as well. So the observations, when the magnetometer is far away from the magnet, it measures a near zero magnetic field on the x direction. What didn't happen is as the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. The position of the magnetometer has no effect on the measured x component of the magnetic field, which is also incorrect. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Well, the code's pretty simple. Here it is. So first we made the dipole definition to return the magnitude of the magnetism. It calculates values based on if it's on or off axis using this model. So we also had to edit the distances, the scaling, and the axis vectors for this code. Here's the model. Given a magnitude of 1.57 times 10 to the negative fifth Teslas, the x component is 0.067 e to the negative 6, and the y component is 2.04 e to the negative 6. And then the off-axis data again. So some what ifs. What if the components of the magnetic field would have been measured as off by a little, since the Earth's magnetic field would have influenced them? Well, this experiment would be the same, but the magnitude of the force would be increased by a certain magnitude based on how large that force is.